Bringing back the mighty mastodon might sound like the ultimate scientific breakthrough, but what if it unleashes chaos instead? These Ice Age giants vanished for a reason, and the world they once knew no longer exists. Behind the feel-good headlines of de-extinction lies a minefield of technical failures, genetic risks, and ethical landmines. So before we resurrect the past, you need to see why this could become science's biggest mistake. Around 10,000 years ago, vast herds of mastodons roamed North America. These elephant-like giants thrived in forests, feeding on trees and shrubs. Then, as the last ice age ended, the world changed fast. Sheets of ice melted, rivers swelled, and forests shifted north. Huge areas of mastodon habitat turned into grasslands or wetlands. Without their familiar woodlands, mastodons lost places to feed and nest. At the same time, humans spread across the continent. Early hunters learned to track big game like mastodons. They used sharp stone tools and spears tipped with fire-hardened points. Mastodon bones and tusks found at ancient camps show people butchered these animals for meat and hides. One mastodon could feed dozens of people for weeks, making them a tempting target. Climate change and hunting pressure combined in a deadly 1-2 punch. Cold-adapted plants that mastodons needed retreated north, replaced by grasses that they ate less of. Populations that tried to follow the shifting forests ran into human hunters. As each herd shrank, genetic diversity fell. Smaller groups had fewer calves each year, and a single bad winter or drought could wipe out an entire herd. Over the centuries, sightings of mastodons faded from memory. By about 8,000 years ago, no living mastodon remained. Archaeologists find the last bones dated to around 6,000 BCE, marking the end of a lineage that began over 3 million years earlier. Once common across North America, mastodons vanished completely. This deep past shows why mastodons are truly lost. Their decline wasn't a sudden flash, but a slow fade driven by warming climates and human hunting. Today's forests and grasslands evolved without these giants for thousands of years. Plants that depended on mastodon browsing changed, as did the carnivores and scavengers that once fed on their carcasses. Mastodons once shaped forests in ways no other creature could. With heads as tall as 2 meters, they pushed through thick undergrowth, breaking branches and trampling young trees. This browsing kept forests open, letting sunlight reach the ground and allowing grasses, ferns, and wildflowers to grow. In spots where mastodons fed, clearings formed, tiny meadows that supported birds, insects, and small mammals. Their massive bodies also helped spread seeds. Fruits and nuts that they ate passed through their guts and sprouted far from the parent tree. Some seeds need the abrasion of a stomach to crack their hard shells. Without mastodons, these seed types could not travel as widely, reducing genetic diversity in plant populations. In addition, mastodon dung enriched the soil with nutrients. Their droppings created patches of rich earth, perfect for seedlings of many plant species. Over time, these nutrient hotspots formed pockets of high fertility, boosting plant growth and overall forest health. Today, forests have adapted without these giants. Deer, elk, and bison fill some grazing roles, but none can push through thick brush like a mastodon tusk. Smaller animals nibble young shoots but avoid the coarser branches that mastodons snapped off. As a result, modern forests often grow denser, with fewer open glades. Seed dispersal also changed. Birds and small mammals now carry many seeds, but they focus on berry-type fruits. Heavy nuts like acorns or horse chestnuts fall near the tree, limiting their spread. Forest diversity narrows when large seed plants can't move long distances. Lastly, the nutrient cycle shifted. Without mastodon droppings, soil patches became less rich. Decomposers still recycle plant matter, but the large, concentrated nutrient deposits once made by mastodons are gone. Forest ecosystems adjusted slowly over millennia, finding new balances, but without the unique benefits mastodons provided. Reintroducing mastodons today would mean reawakening a set of functions missing for thousands of years. Modern forests have settled into a new, steady state. The effects of rebrowsing, seed scattering, and nutrient deposition could ripple through complex plant and animal communities, with outcomes we can't predict. De-extinction of a mammal involves more than just finding old DNA. Mastodon bones are tens of thousands of years old, and DNA breaks into tiny fragments over time. Scientists must piece these fragments together like a jigsaw puzzle, with many missing pieces. Even if they rebuild a complete genome, the sequence gaps and damage can cause errors in key genes. Next comes cloning, inserting that reconstructed genome into a living cell. For most extinct animals, there's no direct egg cell available. Researchers look to close relatives, in this case, modern elephants. But elephant eggs differ from mastodon eggs in size, shape, and cell structure. Adapting the mastodon genome to fit an elephant egg is like putting a VHS tape into a DVD player. Parts may not work. If a lab manages to create a viable embryo, it still needs a womb to grow in. Mastodons shared many traits with elephants, but gestation length and nutritional needs likely varied. Using an elephant mother to carry a mastodon calf could result in growth mismatches, risking miscarriage or harm to the mother. Surrogacy trials with hybrid embryos have shown high failure rates, even among living species. Gene editing tools like CRISPR offer shortcuts, swapping mastodon traits into an elephant genome bit by bit. But editing dozens or hundreds of genes accurately remains science fiction. Off-target edits can introduce unintended mutations, causing health problems in the resulting animal. Every edit needs careful testing in cell cultures before trying an embryo, and each step adds time, cost, and risk. Cost is another hurdle. Building and running a de-extinction lab costs tens of millions of dollars. The facilities must meet high safety and ethical standards, with specialized staff, secure DNA storage, and advanced imaging equipment. Even wealthy foundations find these budgets hard to justify, given the low odds of success. Finally, long timelines slow progress. From genome assembly to birth could take decades of trial and error. Each failed attempt means years of new funding and research. By the time a viable mastodon is born, critical knowledge and technology may have moved on, leaving the project obsolete. Even if researchers overcome technical barriers, revived mastodons would face serious genetic and health dangers. First, older DNA carries damage from radiation, chemicals, and simple decay. When stitched into a modern embryo, these errors can cause broken genes, leading to birth defects, organ failure, or early death. Next, mastodon embryos grown in elephant wombs risk cross-species pathogen issues. Elephants harbor bacteria and viruses that mastodons never encountered. A shared womb could expose the calf to infections it has no immunity against. Likewise, elephant immune cells might attack mastodon tissues as foreign, causing miscarriage or severe illness. Hybrid embryos, mixing mastodon and elephant DNA, pose their risks. Some mammal hybrids, like mules, survive but show sterility or health issues. Mastodon-elephant hybrids could fail to develop key organs correctly or suffer bone, muscle, and cardiovascular problems. The mismatch in chromosome structure may lead to cell division errors, halting development mid-pregnancy. Even a healthy calf could face congenital defects. Gene edits that seem minor, like recreating bigger tusks, can ripple through other systems, affecting brain function or hormone balance. In lab mice, edits in one gene sometimes alter behaviors or metabolism unexpectedly. In a large mammal, such side effects could manifest as life-threatening conditions that appear only years after birth. There's also the issue of genetic diversity. True mastodon populations once contained thousands of individuals with varied gene pools. A revived herd would start from one or two calves, carrying limited diversity. Inbreeding among these descendants raises the chance of recessive diseases emerging in later generations, making the herd prone to sudden die-offs. Long-term researchers would need careful veterinary support, genetic screening, and possibly further gene editing to maintain herd health. That means creating a lifetime of specialized care for an animal that no zoo or conservation park is ready to handle. The financial and logistical burden could dwarf current endangered species programs. Bringing back mastodons means experimenting with living creatures in ways we've never done before. First, scientists would need to create and test embryos in lab settings. These trials often involve test pregnancies that end in the removal of the embryo or the death of the fetus. Each failed trial is a loss of life, a tiny mastodon calf that never gets to grow. That's a form of vivisection where animals suffer for human goals. Next, elephant mothers would carry mastodon calves. Pregnancy is stressful and risky even within a species. For a cross-species pregnancy, the risks soar. Surrogate mothers could face pain, infections, or fatal complications if their bodies can't handle the foreign embryo. Mistakes in timing, nutrition, or embryo size could lead to miscarriage or injuries when the calf outgrows the womb. Each setback harms an intelligent social animal that already faces threats in the wild. If a calf is born, the early weeks would demand constant human care. No zoo knows how to raise a baby mastodon. Keepers would have to learn through trial and error. Mistakes in diet or handling could lead to malnutrition, disease, or behavioral issues. Mastodons might stampede in panic, injuring keepers or other animals. We would be playing parent to a creature without a herd or mentor, likely causing stress and confusion. Beyond the animals themselves, there's the moral cost. De-extinction projects draw attention and money away from pressing issues for living elephants. African and Asian elephants today need better protection from poaching, habitat loss, and human conflict. Using elephants as surrogate moms for mastodons puts their welfare secondary to a high-tech novelty. It treats elephants as tools rather than beings with their rights and needs. Finally, there's the question of consent. We cannot ask an elephant or a mastodon embryo for permission to experiment on their bodies. We decide unilaterally to put them through painful tests, all in the name of reversing extinction. That raises a key ethical issue. Just because we can attempt de-extinction, does it mean we should? Inflicting potential suffering on sentient creatures who only exist because humans drove their ancestors to extinction challenges our moral duty to reduce harm. In sum, de-extincting mastodons risks real suffering, repeated embryo failures, surrogate mothers in distress, clueless early care, and the sidelining of living elephants' welfare. These ethical costs force us to ask whether bringing back an ancient animal is worth the pain it would cause to sentient beings today. Reintroducing mastodons into modern landscapes could shake up ecosystems in unpredictable ways. First, these giants would compete with today's large herbivores for food and space. Deer, elk, and moose already browse shrubs and young trees. Adding mastodons into the mix means less feed for all. Where food is scarce, competition could drive native species away or lower their populations. Mastodons would also browse on tougher vegetation that many current herbivores ignore. In some forests, their trunk and tusk action would break branches, creating clearings. While that benefits some plants, it could harm others adapted to dense cover. Shade-loving ferns or mosses might die off in newly opened gaps, reducing plant diversity. Invasive plants could take advantage of these fresh clearings, spreading quickly where mastodons tear up the ground. Their massive footprints and wallows, mud pits created by rolling in mud, could change water flow patterns. Small streams might shift, wetlands could flood or dry out unexpectedly, and ground-nesting birds could lose nesting sites trampled underfoot. Animals that rely on stable ground conditions, like turtles or small rodents, could find their habitats destroyed. Then there's the risk of mastodons becoming invasive. Even though they once belonged here, today's climate and species mix differ. An animal that eats certain tree bark might kill young trees faster than the forest can recover, altering forest composition long-term. If mastodons favor certain tree species, they might indirectly boost others, shifting forest makeup in a lasting way. Predators and scavengers would face new dynamics too. Big cats of the Ice Age are gone, so modern predators like wolves or mountain lions might not recognize mastodons as prey. If a mastodon dies, large scavengers, bears, coyotes, birds of prey, might feast on the carcass, but they may quickly run out of other prey, causing population spikes that could lead to conflicts with humans or livestock. Finally, mastodon dung could change soil chemistry. While ancient forests gained nutrient patches from dung, modern soils already host new microbial and fungal networks. Sudden inputs of large, nutrient-rich dung might feed invasive fungi or bacteria, shifting the soil food web in unknown ways. De-extinction projects demand huge funds, often tens of millions of dollars. Laboratories need top-notch equipment, secure DNA storage, and specialized staff. Running such a program for years means steady budgets for genome repair, embryo trials, and veterinary care. In contrast, many living species teeter on the brink of extinction with only small grants available. Take the California condor. Once down to 27 birds, recovery efforts cost around $35 million over decades. That funding covered captive breeding, habitat restoration, and anti-poaching measures. Today, over 500 condors fly free, but they still need continuous support for lead poisoning treatments. Imagine diverting that money into mastodon de-extinction. Condors might lose the very aid keeping them alive. Similarly, amphibians face dire threats from disease and climate change. A global amphibian ARC program seeks to save hundreds of frog species with small targeted budgets. Shifting resources to resurrect mastodons would leave frogs, salamanders, and caecilians without critical research or captive care, pushing many closer to the edge. Conservation has limited resources. Governments and donors set budgets for parks, anti-poaching units, and community education programs. When headlines focus on sci-fi feats like de-extinction, public interest and donations may flock to flashier efforts, ignoring the silent crisis of habitat loss that kills countless species each day. Funding mastodon projects also means setting up ongoing care for a revived herd. Costs don't stop at birth. Herds need protected land, veterinarians trained in their care, and monitoring to track health and ecosystem impacts. That could mean millions per year, money better spent on existing wildlife corridors, reforestation, or community-based conservation that benefits both people and nature. Bear in mind, conservation wins often come from simple actions: planting native trees, enforcing hunting laws, or educating local communities. These measures cost far less than cutting-edge labs and yield real measurable gains for endangered species. A single field team can save entire frog populations or reverse habitat destruction in a region, impacts that dwarf the 2 or 3 mastodons a lab might produce in a decade. In the end, funding decisions reflect values. Do we back high-tech experiments to revive one species, or do we shore up the fragile web of life we still have? With so many species needing help now, pouring millions into de-extinction seems like an ill-timed luxury. Real conservation success comes from saving what's here, today's animals and ecosystems that still have a fighting chance. Modern climates differ sharply from the Ice Age world mastodons knew. Today's average temperatures are higher, and rainfall patterns have shifted. Regions that once offered cool, moist forests have become drier or hotter. Mastodons thrived in mixed woodlands with abundant water. In many places, those woodlands are gone, replaced by agriculture, cities, or new forest types unsuited to giant browsers. Land use patterns pose another barrier. Human development has carved up natural habitats into small, fragmented patches. Even large national parks are islands in a sea of farms and towns. Mastodon herds once traveled hundreds of miles in search of food and mates. Today they would face fences, roads, and towns. Crossing highways would risk deadly collisions, while fences meant to contain livestock could trap or injure them. Climate change also brings extreme weather. Stronger droughts, intense storms, and wildfires. A revived herd might face heat stress in summer months, leading to dehydration or organ failure. Heavy rains could flood low-lying feeding grounds, forcing herds into human areas where conflicts would spike. Mastodons can eat tough plants, but they rely on water sources. Drought years could leave them stranded, unable to migrate to better grounds because of human barriers. Moreover, reintroduction sites need vast land areas. Few reserves today cover the thousands of square kilometers that mastodons would require. Expanding protected areas at that scale would mean displacing communities or buying out ranches, steps that face legal and social hurdles. Even if land were secured, fences or patrols would be needed to keep herds within boundaries, repeating the problems of wildlife confinement seen with bison or elephants. Finally, disease environments have changed. New parasites and pathogens thrive under warmer, wetter conditions. Mastodons had no defenses against viruses carried by modern livestock or deer. A single outbreak in a confined herd could decimate the population before it ever stabilized. From technical glitches and broken DNA strands to ethical harms for surrogate mothers, and from ecological shocks in wild habitats to fiscal drains on tight budgets, de-extinction is full of traps. Some experiments carry deep costs with little gain. Some species belong to the past. Here's why mastodons should stay there. Instead of chasing lost giants, let's pour our time and money into saving the creatures still here. Protect forests, fund wildlife care, and help endangered species in real need.